January 2026, the Airbus A350 fleet has crossed 714 delivered aircraft. 1,579 firm orders sit in the backlog. 66 airlines now operate the type, with Turkish Airlines leading at 110 firm orders. Most travelers see only a long white tube with windows. Underneath sits one of the most heavily engineered commercial aircraft in history. Here is what makes the A350 more advanced than almost anyone realizes. The clean sheet design was approved by the Airbus board on December 1, 2006. The original proposal had been a modified A330. Qatar Airways and Singapore Airlines rejected it as insufficiently competitive against the Boeing 787. Airbus rebuilt the entire program from scratch. Development costs eventually reached approximately $15 billion, roughly 3 times the original budget. The first commercial delivery took place on January 22, 2015. Qatar Airways received that aircraft. The structural composition is what separates the A350 from every previous Airbus widebody. Carbon fiber reinforced polymer covers 53% of the airframe by weight. Titanium accounts for 14%. Aluminum and aluminum lithium alloys make up around 19%. Steel and other materials fill the remainder. Airbus states that the A350 is built from 70% advanced materials, resulting in lower weight and reduced maintenance. The use of composites produced 2 specific results. Composite structures resist corrosion in ways aluminum simply cannot. Combined with titanium, the design reduces corrosion-related maintenance by approximately 60% compared to conventional aluminum aircraft. Carbon fiber also tolerates higher cabin pressure differentials without fatigue cycling damage. The wings are among the largest single carbon fiber structures ever produced for commercial aviation. Each wing flexes measurably during cruise. The flexing reduces drag and absorbs turbulence loads that would stress a rigid metal wing. Wingspan reaches 64.75 meters, wing sweep measures 31.9 degrees. Curved winglets at each tip reduce vortex drag at high altitude. Power comes from the Rolls-Royce Trent XWB. The A350-900 uses the Trent XWB 84, producing 84,000 pounds of thrust. The A350-1000 uses the larger Trent XWB 97, generating 97,000 pounds of thrust. Airbus credits the engine and airframe combination with a 25% reduction in fuel burn and CO2 emissions versus previous generation wide-body aircraft. Performance numbers reflect the design priorities. The A350-1000 reaches 16,700 kilometers or 9,000 nautical miles on a single tank. Cruise speed sits at Mach 0.85. Maximum takeoff weight stands at 322 tons. Maximum fuel capacity reaches 168,300 liters. The underfloor hold accepts 14 cargo pallets, or 44 LD3 containers. The aircraft is 73.78 meters long. Singapore Airlines uses an ultra-long-range A350-900 variant for its Singapore to New York service, exceeding 9,500 nautical miles. That route, the world's longest commercial flight, exists because the A350 was specifically engineered to support it. The cockpit centers on a flight management system built around high-resolution displays and extensive automation. Pilot training reflects the cross-fleet commonality with the A330. Pilots transitioning from the A330 require only 8 days of training to fly the A350. A380 pilots need 5 days. A320 pilots need 11 days. A pilot with no Airbus type rating requires 24 days for full certification. The aircraft produces thousands of operational data points during every flight. Onboard systems feed the Skywise platform, which Airbus describes as the industry data platform purpose-built to address aircraft operations challenges. The platform analyzes performance, fuel burn, and component health data across global fleets. Airlines use the system to schedule maintenance before components actually fail. This predictive approach has reduced unscheduled downtime across operators reporting performance data. The cabin width reaches 5.61 meters internally, with a fuselage diameter of 5.96 meters. That measurement runs 13 centimeters wider than the Boeing 787 and 33 centimeters wider than the A330. The extra width allows 9 abreast seating in economy with twin aisles, or wider premium seating in business and first class. Standard 3. Cabin pressure is maintained at an equivalent altitude of approximately 6,000 feet, lower than the 8,000-foot standard on older aluminum wide-bodies. The lower altitude correlates with measurably reduced passenger fatigue on long flights. Cabin humidity is maintained at around 20% compared to 4 to 10% on previous generation aircraft. The higher humidity is possible specifically because composite structures do not corrode under sustained moisture. The aerospace cabin adds the quietest twin-aisle environment in commercial production, latest generation in-flight entertainment, and high-performance air filtration. The A350-1000 offers 40% more area for premium category seating than direct competitors. As of April 2026, the A350 program had received 1,579 firm orders from 66 customers. Of those, 714 aircraft had been delivered. The A350-900 accounts for 1,111 orders and 601 deliveries. The A350-1000 accounts for 367 orders and 113 deliveries. The list price for an A350-900 sits at approximately $317 million. The A350-1000 reaches around $366 million. Airbus delivered 57 A350s during 2025. On October 17, 2025, Indigo finalized a firm order for 30 additional A350-900s, extending the program into long-haul operations from India. The A350F freighter variant continues to take orders against the future cargo replacement market. In May 2026, Airbus notified A350 customers that some deliveries scheduled for the late 2020s will be pushed into the early 2030s. The delays reflect supply chain constraints rather than weakening demand. Airbus reported a total commercial backlog of 8,754 aircraft at the end of 2025, the highest in company history. The wide-body share of that backlog reached a year-end record of 1,124 aircraft, of which 830 are A350s.